Okay, so let's see, I've got these two chats here. All right, cleared those. All right, I see that several people have turned in lab reports already, and I've gone through a couple of those and taken a look, and it sounds like things are going okay. So we're going to go over things like entities, attributes, resources today, but we already got a little bit of intro of that in the lab stuff, and you'll get more practice of that at homework B1 as well. So any questions about how things are going so far? Anything I can answer before we keep moving? All right, so reminders here. For those working ahead, homework B1 and lab 2 are available. Read chapter 2 before lecture B2, which is I think a week from today. And then ICA B2 will also be due before lecture B2. So those are, there's actually, it took off the time limit here. Apparently I didn't adjust it on this slide. So there's just 5 questions that will relate to this chapter 2 content, basic simulation concepts that we'll see here. So that's what we've got going forward. And so today, we talked about introduction to modeling more broadly last time, and now we're talking about simulation in particular. So if we remember from last time, I think the way I've got this shared is just a little bit slow. We talked about that as industrial engineers, we have to build knowledge about the operation of large, complex mixtures of humans and technology. So we don't have the benefit of the science already being done for us. We have to do the hard work of experimenting on real systems or surrogates for real systems to build knowledge that we can then make use of the same way a chemical engineer would make use of a chemistry textbook. So, so we sort of are this weird combination of science and engineering together, kind of right there in the middle. So we, just like other scientists, have to develop and study models. And so the models that we build are there because we're trying to come up with the F equals MA for industrial systems. And so, you know, so then we had to say, well, then what the heck is a model? So we have to kind of better understand that. And my claim was that everything on this slide is a model, from the fashion models to the animal models to the Bohr model of the atom. They all are flawed, inaccurate in some sense, but very useful. I just linked a video online that actually my wife is teaching a basic introductory class on biology, and they're going through electron levels and things like that. And I just happened to overhear her, one of the videos that she posted, and I ended up posting it myself. And what I thought was great about this particular person who put together this video talked about how the Bohr model was a very useful in that it helps to explain why when you hit atoms with a certain amount of energy, they give light away and all that, but is now viewed as very inaccurate. And so I thought it was, you know, sort of perfect to kind of go along with this, and that was just coincidental there. And so like each one of these things maybe puts us in a better place than we were before we had the model, but certainly leaves things out, maybe gets a few things wrong, and so on. And so we have to really appreciate that there's always going to be a reality gap between our models and the things that we're hopefully working in. But the key point to those models is not their accuracy, it's how well they help us answer these what if questions. So what if I made this process improvement? What if I put something on the left instead of the right? And so on and so forth. Anything that helps us answer a what if question is what I'm calling a model. And so we in this class build simulation models, artificial models that help us gain understanding before experimenting on the real world. Because we, you know, anytime you deploy something in the real world, you're going to gain knowledge that is going to help you answer a what if question. What if a boat built like the Titanic goes into frigid cold waters? Well, we learn a lot from that the metal becomes more brittle and so on and so forth. And then that ends up helping us in building the next set of boats. But we don't want to, you know, get things wrong in the real world a bunch of times as our only avenue for generating knowledge. And so we try to build something similarly complex as the real world in a computer system And that's what we kind of do in this class. So trying to build those sim models. Now in building those simulation models, we are necessarily going to leave stuff out. And when I define stochasticity today, then it'll be a great example of what I mean by leaving stuff out to actually increase the realism or increase the generalizability. So rather than building a precise model of the Titanic every single time, we can say, well, what are some general properties that the Titanic shares with other boats? And is there anything we can learn more fundamentally about these boats that maybe makes it easier to implement as well, that also makes the lessons learned from simulation apply to a much wider a range of systems? And the way you get generalizability is often by decreasing in those realistic details. So it's another example of how the simulation models you build will necessarily be lacking in some sense, inaccurate, imprecise, because we do that for computational tractability, just getting them to run. Then we also do that because it oftentimes increases the generalizability. So if I'm building a model of a classroom, I could choose any classroom and I could say, all right, this is my model classroom that I'm using the classroom as a model for all classrooms, and then I'm going to build a simulation model that only uses these dimensions, these sizes and everything. And that gets me so far, but there might be something peculiar about this classroom that doesn't apply to other classrooms. And so if I build all of my knowledge around this classroom, I might get a lot of things wrong when I try to implement in another classroom that maybe has tables that you all sit around as opposed to sitting down these rows. So, and vice versa. So we're always going to make some compromises to try to get that generalizability. So in this class, in order to do all of that stuff, we're going to start with some mathematics, probabilistic modeling. We're going to combine that with some programming. How do you get those probabilistic models into a computer? They can help do a lot of the really heavy lifting for you. And then when we get the stuff out of that computer, we're going to generate data, and that's what the statistics will be for. So I don't want you to think of this class as just a programming class, certainly not just an arena class. Arena is not the be all and end all of simulation platforms. It is a platform we chose for this class that is very similar to FlexSim and all sorts of other platforms that you might see on internships or in your real jobs. But once you learn how to build things in Arena, it will be very easy to learn how to build things in FlexSim and et cetera. These concepts of entities, resources, et cetera, those are generalizable. So even Arena, I view as a model of how you do modeling. It might work for you if you happen to go to a company that uses Arena, but if you don't go to a company that uses Arena, we will try to highlight aspects of Arena that aren't special to Arena, that maybe don't squeeze Arena for all of the cool features that it could possibly offer, but helps us generalize to other models. So it's not just a programming class, and even to the extent that it is a programming class, it's not just about Arena, but really this class is about surveying how all these things come together, which means how do we use the stuff we know about probability, the stuff we know about stats to build useful models that run relatively quickly on computers. And so that is, and then good statistics are going to be important for both of these things. So we cram all of that into 475, basically before the midterm, during the lab, after the midterm. It's kind of how things are structured here. But if any of these things seem particularly interest to you and you do want more specialized knowledge in these, then there are more specialized courses that you can take later on in your career as professional development or in grad school that focus on just one of these things. But for now, we're kind of giving you 3 legs for this table to stand on so that you have a stable foundation and how these things come together for simulation. So that's what we're doing this semester, and that's roughly our introduction to kind of modeling and where we're going. So before we get into the specifics of simulation, any questions about any of that? We'll also glance over at the chat here. Anything is pretty clear? All right, hopefully right now seems very abstract, but also, not too difficult to grasp. All right, so sim. So there are 3 major simulation methodologies. We focus on one of them in this class, but we will at least have some exposure to this other one here. So I'll go through those here in a second. But if you've known anybody who's taken 477, that is another simulation class where they focus on system dynamics modeling. And so we'll kind of talk about these three here and how they fit together and why you might use these things. So like I said, 477 focuses on system dynamics modeling. This is a very popular modeling technique you see in ecology, you see in business. W.P. Carey has classes on system dynamics modeling. These models are, if you've heard of the SIR model for modeling epidemiology, that's kind of fits into this class of models. So these model the kind of average and macroscopic behavior of systems. And so we're not interested in the kind of day-to-day details of an individual in a system. We're interested in looking at populations over long periods of time. So they're interested in, so how do general causal interdependencies explain trends or patterns? And so, you know, if the case of an SIR model in epidemiology, there's a group of susceptible, a group of infectious, a group of recovered individuals, and you're interested that in what is the trends in these three slices of the population over time. Given you have a lot of susceptibles and very few infectious, on average, how are the susceptible and the infectious population going to change over time? We don't care necessarily about any particular susceptible or any particular infectious individual, but we care about how many there are over time, and we care about the average. Over many universes, on average, what's the average behavior across those universes? And so we don't model the individuals like large scale counts of individuals with some shared property. That's system dynamics modeling. The advantages of this is, you know, you get a lot of generalizability by giving up all those details. So this is another one of those cases where by simulating things at a mile high perspective, at a population level, with like blurring out all of the individual details. So looking down on the ground and seeing everybody, just seeing cars just as lines as opposed to individual cars. It's very fast to simulate, requires very few parameters. So it ends up being very generalizable. So you don't have to customize it to a particular city or a particular room, those sorts of things. The downside of this is it doesn't capture a lot of the small scale details that you might want to know. So if you're running a hospital, you might want to know, how often do we go over some threshold of patients in that hospital? You don't want to know on average how many patients we have in the hospital. You really want to know these extremes, and the extremes aren't going to be captured in the system dynamics model because it's just kind of the average. So that's one of these kind of simulation methodologies. Now, so what does a system dynamics model look like? So here's an example. This is a marketing example, kind of a famous marketing model, the BAST model of innovation diffusion, where you've got a group of adopters here, potential adopters. These are people who haven't bought the iPhone. And then you've got a group of adopters, people who have bought the iPhone. And what this graph is showing you here is if you start with a bunch of adopters and a little bit of word of mouth, or sorry, a bunch of potential adopters who haven't bought the product yet, and a little bit of word of mouth, then you can get a rapid rise in the adopters, but then eventually you reach market saturation and it falls off. So that growth doesn't go forever. So you get this sort of S-shaped growth where these graphs kind of capture here. You end up getting the adopters kind of peak out. You get this maximum pickup of adopters, but then they fall off after that. And so you get this, if you actually look at how many adopters you have, so these are the people adopting, these are how many adopters you have, it starts at 0, rapid rise, and then levels off. So this is an average behavior of a market that, in this case, it's been programmed in this kind of graphical way where you create a compartment of potential adopters, a compartment of adopters, and a process that translate potential adopters into adopters based on how many individuals are in each group. And that's how system dynamics modeling works. You create these compartments, you say how these compartments relate together, and you get these average behaviors that come out of that. So that's something that you might see in more detail if you were to take a class like 477. I also teach a class in sustainability, SOS 212, where we use this same modeling approach to our sustainability problems. And here's an example model from system dynamics modeling for an airport. And so they've, if you were to, I'm not going to spend a lot of time on this, but basically they start identifying all the causal connections that generally cause, that cause trends to move around. So in general, what causes people to be late at an airport? And you can kind of come up with a bunch of those things and say, well, this thing has a positive influence, this thing has a negative influence. And you build one of these so-called causal loop diagrams. You can translate one of these causal loop diagrams into a stock and flow diagram, which is these things that have these thick valves that are going into these stocks, and then these interrelationships. And then this is actually how you program the model. And this behind the scenes builds a little differential equation that the computer sim integrates, forward integrates to get those graphs that come out of that. And so after you put this into your sim, you hit play, it ends up building that, it ends up building that model. And so then you end up getting the this sort of long-term trend where you can say at 3 different types of parameters. So I'm going to adjust this aspect of the airport, this other aspect of the airport, this other aspect of the airport over long periods of time. Then what is the kind of accumulated delay that I get? And it's a way to compare these things. But you're just comparing averages. You're not comparing the maximum delay you could get at an airport or the minimum delay. It's just sort of the average delay you might get relative to some baseline at this airport. So that's kind of an example. So this is meant to be a very high level example of the point that I'm trying to get here is that system dynamics modeling is all about the averages, the long-term behavior. It is not about modeling the individual. Now we can contrast that with agent-based modeling, ABMs, or individual-based modeling, IBMs. It's the same thing. In agent-based models, you are modeling the microscopic behaviors of every single individual as they bump into each other. So rather than saying a formula for I have this many susceptibles and I have this many infectious, on average, I'm going to get this many susceptibles changing to infectious. Instead, you actually model an individual. This individual is currently susceptible. This individual is currently infectious. And when that, and I'm going to have them move around in space. And in a virtual world, when they move around in space, occasionally they'll bump into each other. And when they bump into each other, there's some probability that the susceptible will get infected by the infectious. And you can then sort of do bookkeeping to see right now, based on how many individuals are currently susceptible and currently infectious, what do those demographics look like? And if I rerun the simulation over and over again, I get different results because they might move around in slightly different patterns. So it is much more sort of realistic because you've got all these interacting parts, but it adds a lot of complexity. So you model what happens at every event of an interaction, but you don't quite know what's going to happen when you put everything together. That's why you have to do the sim. So these are often spatially explicit, where the space, the fact that they, like in this case, the effect of these doors on our flow, you could build an agent-based model that would really sort of help us get a better idea of how quickly people could move out of this room, because we could have them moving around and seeing that there's going to be congestion at that door. And rather than trying to build a mathematical formula to understand the kind of fluid-like congestion at that door, we could build an agent-based model that might be a better model for real people than a fluid model. Because, like we get jammed up like a granular media, whereas, a water fluid is, at the micro scale operates very differently. So if we use the fluid flow model, then maybe this like aperture isn't going to work out, but our agent-based model would allow us to maybe get better stats on what really happens when all of us try to rush through to that door. So space is often really important in these agent-based models. So an advantage here, very realistic, but with the increase in realism, slower to simulate. The models can be difficult to understand because they are just as complex as the real systems. And there's a large number of parameters which make them sometimes very difficult to generalize, because building a model for this room that's perfect for this room totally gives you no insights about the room next door. So that's an agent-based model. So those are two sort of opposite ends of the spectrum, where it's high-level macroscopic and low-level microscopic. So before I go into what we focus on primarily in this class, are there general questions about these two extremes? Does that make sense about these these basic ideas here. One's very math driven, the other one's very sort of sim driven. Like all of them involve a little bit of computer. The computer makes the math easier for the system dynamics modeling. In the agent-based modeling, there really is no math to fall back on. It really is, you can only get these things done with the computer simulation. There's no equation to integrate. So any questions about that? And you'll have exposure to this in lab 4. You'll get to see a couple of agent-based models and play with them and get a little bit more background, because this is growing as being more and more important for industrial players, but our curriculum traditionally doesn't reflect a lot of ABM. So I've tried to make sure to at least give you one lab in ABM. Okay. All right, so then what we focus on in this class, so I've got some examples here of ABMs. So just a couple of off-the-shelf examples. Agent-based model of a city where you've got this sort of prototypical city with intersections, red lights and green lights. You can study traffic patterns. Disease spread, you got people moving around an unbounded area, some of them infected, some not. You can see how space affects the flow. So you could imagine putting out quarantines, and if you can manage to get people infected in a quarantined area, it would affect the flow of the disease. And then things that are not quite as motion-based, but you can have networks of, say, generation, storage, and consumption of electricity, where you get different types of agents, consumers, producers, transmission, and you can say, well, you know, they've got these demands might be coupled in some way. So in the middle of the day, they're going to be higher. In the middle of the night, they'll be lower, but they're going to have some differences between them. And so studying the heterogeneity of demand and how that's going to affect the supply challenges, something you could do in an agent-based model. And so if I were to show an example of an agent-based model running, another airport example. So here's an example that I'll animate here in a second, but this is kind of a trivial example, but you've got a bunch of people arriving to an airport here. They're trying to get through security gates here. Some of the security gates are open, the green ones. Some of them are closed, the reddish orangish ones. And you've got stats on how many people are in the metal detectors, how many passengers are in the system or have left the system. And so you can, you know, study the speed of how quickly people get through this system. And over here, you can turn on and off those queues. So you can say whether Q1 is on or off. You can switch these and that'll turn them from red to green. And so if you simulate this sort of thing, it doesn't quite look like a real airport. It does look like it has interesting dynamics, but the question is, are those dynamics at all realistic? I mean, there is a universe out there where maybe airports might look this way, but maybe it's not our universe. Because you see them milling around out here, they randomly hit a gate, then they move through the gate at some speed, and they get out, and then they're moving out of here. Now, so, and you can again, you see the mouse moving around, turning on and off queues, and it's affecting the dynamics of things down here. So you say, well, why is this potentially useful? Well, a lot of times these agent-based models are useful as null models of system behavior. What I mean by that is sometimes somebody will build a interesting operational strategy and they'll run it for you. And in that operational strategy, they'll say, look at this great pattern that we saw in these metal detectors. There was a spike initially, and then eventually things fell off, and they fell off very quickly. So we think that's a good sign that our operational strategy is working well. But you always need a benchmark, right? And so these agent-based models can often be a good benchmark. And then you can say, well, what is the null expectation? What would happen at random? Just that if people were to just arrive at these things and then just mill through whenever they hit them first, like that's not how we operate an airport. But we can use that as kind of a baseline behavior that we want to do better than. So we can run the agent-based model in this kind of unrealistic setup to get an idea of what the baseline case would be, then implement the novel operational strategy and see how much it differs. And if it doesn't differ much at all, then we'd say, well, you know what? I don't actually think that you've made much of an improvement, but if it does make an improvement, then maybe that suggests we should move on to more detailed analysis, like implementing it as a test case in some airports out there. So does that make sense what I mean by using it as a null model, a baseline case for what to expect? So you actually purposely build a very trivial solution that is not the solution you'd want to implement, but you use it as baseline performance on which to gauge whether a strategy you might use is a better strategy. Does that make sense? Okay. All right, so that's ABM and SDM. So what we focus on in this class is discrete event system simulation, sometimes known as process-centric simulation. And so this you can view almost as a blend of those two extremes. It falls in the middle. So we do model individuals, but we don't give individuals agency. So an individual doesn't decide where that individual is going to move. We give those individuals a map, kind of like this one in this little diagram here. And then those individuals must be shoved through that map. And the things in that map decide the possible places that those individuals can go. So individuals are created in some place, and then they have to go through some box, which delays them by some random amount. And then they have to go into a decide block here, where some individuals will go back through that box, whereas other individuals will end up getting to proceed through the system. But the individuals aren't making any decisions here. The individuals are just placeholders that we keep track of. So we could imagine painting these little marbles red and green, and we could ask, how long does it take the red marbles to get through the system? How long does it take the green marbles to get through the system? And so our focus is how we design the system and assume that the system shoves these marbles around, and then we don't do stats on these marbles. How long were the marbles waiting before they could actually enter this block, et cetera? So, so these here, this is where those terms, entities, resources, et cetera, the entities are the marbles that are moving through the system. The resources are the things that are fixed in the system, that if all the entities came and all the entities went, those resources would still be in the system. And the activities are the durations that each resource is tied up with while handling an entity. So if I enter a kitchen, I might want a cup of coffee. It's going to take me a certain amount of time to make that cup of coffee, but I can only make the cup of coffee if I can find a cup of coffee. So there might be 10 cups in that kitchen. Well, that's going to be a resource with a capacity 10. So I can take, well, if none of those resources are available, I have to sit in the kitchen and wait for someone else to finish their coffee and wash the cup. And then I can go and then start my coffee. So there's a delay while I'm waiting for the cups to be available. The cups never leave the kitchen. It's like a faculty break room or something like that. So there's a bunch of cups in the break room that you can use if you can find one, but you can't take it out of the break room. So those cups, even though they're being moved around, they never leave the system. That's why that makes them a resource, because you have to wait on them. But the people entering the break room are the entities. And so they have to sit and wait for cups to be available. And once they're done with their cup, they can leave the system. So the things coming and going, those are the entities. The things they're waiting on, those are the resources. And we'll go into that in a little more detail here. But that's sort of the main modeling approach behind discrete event system simulation, is figuring out what are the entities, what are the resources, and how are they all connected together here. So, how individuals arrive to the system and how long each resource spends with each individual are the key modeling parameters that we're going to model probabilistically. We're going to come up with distributions for these things that, and we'll motivate why we use randomness as part of the way we do this here today. The advantages to this is that it's more realistic than system dynamics modeling, because you do get individual level variation, but it's much faster to simulate than agent-based modeling, because it's not quite as a complex mess of individuals bumping into each other and interacting. And it's a really good fit to a lot of engineered systems where we, as engineers, have sort of sculpted the system into a particular process. So agent-based modeling is very popular in, say, ecology, where you got a forest. You have no idea where an animal is going to move in that forest, but it can move anywhere in the forest. Well, that's a great agent-based model. So you have to come up with a model of foraging motion for that animal as it moves through the forest and allow for anything to happen. And that's worse. But when we build buildings, the built environment here, airports or whatever, we pretty much can count on people moving in one direction, moving from one place to another place. So we feel that we can structure the process reliably, and that's why DES modeling ends up being very commonly used in these engineered systems. But the downside of these is it does require some background in stochastic modeling and probability. You guys, this is the 400 level class versus the 200 level system dynamics modeling course, or some of the agent-based modeling that also can be done with people who don't have any quantitative background. So it does require a little bit more sophistication in the designer to build these discrete event system simulation models. Okay. All right, so I want to give an example of one. So here's an airport example. This is built in Arena. So you could, passengers arrive to security here. Those are the passengers or the entities. They then will go through a process where they get, before they can go through anything else, they have to check for proper identification. Some of them will pass security and move on through the airport. The other ones will be denied. And in this model, which is inaccurate, but at least gets us partly there, they're just kicked out of the system, denied, sorry, go away. So that's our basic model of this airport system. Now, I can take this, and in Arena, I can implement that and add a little visualization of a security checker here with a little front of the line here, and I've got a queue where individuals are going to line up. So I can actually visualize what's going on inside this process diagram right here, and it looks like I've added a spatial component, but I'm not actually formally modeling the effect of space like I would in agent-based models. I can also then say, plot the work in progress, plot the WIP over here, and I can see that I'll get realistic variation out of this thing. So I build this little model, and then I move on, and I can start to simulate it. And what Arena will also allow me to do is take this 2D version and actually build a 3D version down here, where I've actually got my document checker is a 3D document checker, and my entities are 3D entities. And they're lining up. You can see them lining up in 2D, they're lining up in 3D. They spend some time with the document checker. Some of them get to go through, some of them are kicked out of the system. And you can watch the WIP here is getting more, you get realistic variation in how many entities are in the system at any particular time. And if you're to look closely, my mouse, as I'm recording this, I'm dragging up and down the speed of the simulation up here. So I can slow this thing down, watch things go slowly, I can speed it up, I can drill down into the entities and ask about the entity's history, like this entity seemed to have really bad luck. What's going on with that entity that made it have really bad luck? And so I can do those sorts of things. So these are the types of models that you'll build. This is an airport example. I can also show you, so I think a little box will pop up here. So it's not spatially explicit, but this visualization makes it look plausible to our stakeholder. So if you just show your stakeholder the flow chart, stakeholder might say, yeah, that makes sense to me, but I just don't buy it. But if you say, okay, well then let me visualize this for you. And they say, you know what, this looks plausible. I see this in an airport. And so I'm actually, I now better understand your flow chart now that I've seen it in 3D. And then similarly, here's a hospital room. I'll pop up here in a second. And in this hospital room, it's a similar sort of idea where you've got this 2D visualization. Cars come up to the ER department, they pull in, they drop off people, they go to this receptionist. Some of them then end up waiting in a lobby area. Eventually, after waiting, they go into another waiting area. After waiting there, they get issued to beds. Different things happen at these different beds, and eventually they move out of the beds, freeing up the beds for others. So you can see this, to me, from a bird's eye view, looks like a very plausible realization of an ER department. There's a lot of realistic variation. Average total time in system is being plotted here. In the actual model, I haven't actually done anything that's spatially explicit. These individuals walking around, they only can go to the receptionist, and they only can go to the lobby, and they only can go to one of these spots, and they only can go to one of these spots. So I leave out a lot of the details of them actually walking around, going from place to place, but I can add randomness that sort of accounts for the fact that not everybody walks from one position to another position in exactly the same way. So it simplifies the modeling burden on me, and I still get a relatively realistic system. And I can get all sorts of realistic stats out of that. So I've got, the type breakdown of conditions, the number in the system, the throughput for different types, for critical versus excellent, and so on. I've got the number, resources here, how many beds do I actually use on average. I can get all sorts of really realistic model output out, even though the models that I'm building don't look much more difficult or much more complicated than simple flowcharts. So patient rooms, this is a process of securing a bed, delay for prep, secure a nurse, delay for nursing help, and so on. Like, it is a recipe that every individual will follow some variation of. And our job is to go into each one of these boxes and add realistic variation. We don't have to add all the Phoebe Bridgers quotidian details of exactly why they, took a little bit extra time, with this nurse. We just know that sometimes it takes shorter with a nurse, sometimes it takes longer with a nurse. So we're going to draw from a random distribution and put that in there. So every entity will go through the exact same flowchart, but they'll spend different amounts of time in different processes here. And when a process is a resource, that there's a limited number of them, then entities behind other entities may have to wait to get into that resource because the entity in front of them just happened to take a lot longer in that resource. So that's kind of what we're building here in this is kind of emergency department model. And we can add a lot of embellishments. So this is that airport example going back to here. This is that front end that I just showed you. We added a bunch of other stuff out to the end of it. So this is the X-ray. There's other, so not only did they pass security, but we also added the X-ray process here and whether they got through the X-ray machine. And again, it's just a simple flow chart where the variation is built into aspects of the flow chart as opposed to the flow chart itself. So an agent-based model, the flow chart emerges from the interactions. In a discrete event systems simulation model, it's always the same flow chart, but the variation emerges from choices we make in the particular nodes of the flow chart, as we'll see throughout the semester. All right, and then, like I said, I can get realistic variation. I get waiting times that have averages and half widths. I get utilizations, which themselves, vary from simulation run to simulation run, and so on. Used in a lot of industrial applications, so modeling factories, things like that. It's also used in a lot of not so industrial applications. So I think I have an example here where they used ARENA to model the optimization of gleaning for food banks. So they were trying to figure out, how do you allocate volunteers to go out to farms that have a bunch of waste food? It's still pretty good, they just aren't going to harvest it and sell it. So the volunteers go out and they need to gather this stuff up and then distribute it at food banks. And so the question is, how do you best allocate the available volunteers to the randomly available food at these farms? And they built an agent or a discrete event system simulation model in ARENA to help them try different ways to optimize this, and apparently had some success. So I've got a link to this in the Unit A module on Canvas. So, and so this is their this is their discrete event system simulation model, again, built in ARENA for that same time. All right, so that's sort of the basics of DES. Before we start going down into the details that you've seen and that we started to work with in the lab, and you'll see in the first homework, and start motivating why we use randomness. Are there any general high-level questions about these three modeling types, about discrete event system simulation, or comments or thoughts? Our goal is realistic variation that can run efficiently in a computer and give us generalizable insight across a wide range of real systems. So they're getting, what about the stats on the station?
We have the creative station in ARENA. We'll give it information about how the station functions and run and do its thing.
That's right. So the question here is like, so generally what the process would be, would you build like a station in ARENA, give it stats on how the station runs, and then run it and then sort of see what the outcome stats are? And it is kind of like that, but it's like we're going to have metrics on how every tiny part of the system works. And then we're going to put them together and they're going to weave a tapestry of all of those parts together. So I know I can go out with a stopwatch and say, on average, this document checker takes 30 seconds to check this document. I know on average, when you lay a piece of luggage on this conveyor belt, it takes an average of a minute to get through. What I don't know is when I put all those things together, how do these different waiting times align? And so that's the thing that the computer simulation is going to help us with, is how to put these things together, because most likely the activity durations in one case are not going to necessarily line up perfectly to another. So that's what the purpose of the simulation is to then generate stats on all the mismatches in the activities that are out there, because we just can't synchronize. I mean, anybody who's driven, on a street knows that, you don't always get that green wave where it's green light, green light, green light, green light. Eventually, you get stuck at that red light because your timing doesn't quite line up with the city's timing. And so how long do you wait at the red light? That's something we could model in the computer simulation on average. All right, other questions about where we're going with the vision here? Questions in the chat? Okay. All right. So let's do, I'm going to skip the first attendance exercise here just to move on. So that is a null attendance exercise here. For those of you who, you don't have to install Arena yet. We don't start using Arena until Lab 5. But for those of you who want to move ahead to install Arena, make sure to follow the installation instructions that I've linked from Canvas, because Arena, the textbook, so back in December of last year, they made a major change in the user interface for Arena, and they labeled it, they went from 16.0, which is the version that's like the textbook, to 16.1. That doesn't sound like a big change, but it was a massive overhaul of Arena. And it just happened in December. We don't have any fresh textbooks. We don't have any fresh curriculum materials. All of the same stuff is in Arena, but it's located in slightly different places. And so it takes a little bit of a search. Fortunately, I know where everything new is. The TA knows where everything new is. We can help you with this stuff. But that's one thing that if you look at your textbook, you'll see things that look like this. If you look at the new version of Arena, it looks a little bit different. It has a ribbon across the top, like Microsoft Office programs. And so it is a little bit nicer of an interface. One of the downsides is, we could have told people to, we could have left the old version of Arena installed on all the labs, but I know some of you would have just gone to Rockwell's page and downloaded the newest version of Arena. Models that you save in the new version of Arena will not open in the old version of Arena. The other way around works. Models you save in the old version of Arena do open in the new, just not the other way around. So that's why we made the decision just to keep everybody on the new version of Arena and deal with a little bit of those headaches. So that's one thing there. The other thing is when you install Arena, due to licensing issues, I guess, the old version of Arena would naturally install automatically something called Crystal Reports Engine. The new version of Arena, you have to manually install that. They give you the installer, and I've got these instructions on the online instructions here on Canvas. They give you the installer, but they're not allowed to, I think, run it for you. So you have to go into a folder and run the installer yourself. And then once you run that, so you install Arena and then Crystal Reports, then you'll be able to get the reports that we expect when we go through textbook and lab exercises and so on. But it does require this one extra step. So I'll remind you of this as we get closer to Lab 5, but for those of you just moving ahead, I just want to say it to you now, Arena 16.1 looks a little different than Arena 16.0 and requires this extra installation step. So look out for that. Okay, so looking forward, most of you, I think you didn't have to go to lab yesterday, but so if you haven't gone to lab, you should look into lab because that'll be due Sunday. And then, so your first homework will be coming up. It's assigned on Tuesday. So the terms that we're going to go over here are going to help you on the first lab as well as that homework there. So those general terms. System, I've used this term a lot so far. I'm just going to call a system a group of objects connected for some joint purpose, and you as a modeler have to decide the boundary of the system. So you decide exactly how many elements you're going to put in that system. So as an example, if I'm modeling a classroom, if that's my system, you know, it has 100 students in it with an instructor, there's it's a lot different than modeling an entire campus. And so both of them are systems, but if my question is at the level of a classroom, then I don't need as many details that I need at the level of the campus. So you technically could ask research questions about classroom operations using a model of a campus, but that model of a campus might have tweaks in it, which really optimize it for asking larger scale questions. Or it might be specialized for a special time, like modeling campus during the summer where there's fewer classes. So, so you're choosing the boundaries is a big part of your system. But just a system is just a general term we're saying for a group of objects connected for some joint purpose. We deal with dynamical systems in this class, which are systems which change over time. And a dynamical system has the notion of state. So the state is the thing that is changing over time. So the state is the current value of the system. The system moves from state to state. And so, for example, you might have 5 passengers in a waiting line now, but then, so that's the current state of the system, but a little bit later, you might only have 4. And so the system moves from a state where you have 5 waiting to a state where you have 4 waiting. And so that's what we mean by state. It's the current snapshot of the world of the system. State variables are the things that we use to keep track of state. So there's a distinction here between a state and a state variable. So the number of passengers waiting in line, in quotes, that's a state variable. X, we might call that. That's a state variable. X could take on a number of values, and those values are each states of the system. And we're going to refer to discrete state variables, which in this class are state variables that only change at countable instants of time. So the temperature in this room changes continuously. It doesn't only change on at an instant. It's you could measure the temperature, and as you zoomed in at any time scale, you'd see it changing. These systems that we work in for this class, the state variables or the states only change at discrete instants of time. Those aren't clocked instants of time, but whenever you see a state change, you're going to see a single jump to another variable, another state. The variable will jump from one state to another, and then there'll be another jump down. So if you zoomed in far enough, you would see no changes. So that's the idea, is that you can look for the particular parts or points where the state changes and count them. And if all of those are in a countable set, then we refer to those as discrete state variables. So that's what we talk about, discrete event system simulations. What we mean by discrete event systems are dynamical systems whose states only change at discrete time points that we refer to as events. So an event is the instant at which a state changes. So are there questions about those distinctions? System, discrete variable. And that'll become more clear as we start seeing more examples of these systems. And so, okay, moving on. So basic process definitions. Some of you should already have some exposure to this from the lab. I already talked about this a little bit earlier. Resources are components in limited quantity that are used to execute activities. So resource availability can change over time, but the resources are not viewed as arriving and departing. So it might be the number of coffee cups goes from 10 to 4 because 6 of them went in the dishwasher, but we don't view them as having left the system. We just view the resource capacity change from 10 to 4. And later, when they come out of the dishwasher, it goes back from 4 to 10. But the resource didn't arrive to the area and then leave. It just changed its capacity temporarily. So capacities can change over time, but the resources, like the placeholder for them, is always there. So that's something special about resources. So X-ray scanners, TSA officers, boarding pass kiosks, etc. these are things that are always in the system, even though they might temporarily go down, but they'll come back up again, and they're sort of always kind of there in spirit. The other type of thing we worry about here are entities. Now, these things do arrive and depart. The people going into the break room, the people coming out of the break room, the passengers going into the airport, the passengers going out of the airport. These entities are delayed when they can't find a resource. So when they're in a resource, they're conducting an activity. When they're waiting for a resource to become available, they're in a delay. So there's a distinction here between activity and delay. So passengers, luggage, etc. Okay, attributes. These are things that help us differentiate between different types of entities. I'm wearing a black shirt. You might be wearing a yellow shirt. So that's an attribute of us. And so people wearing a black shirt might be treated differently than people wearing yellow shirts. And so later on in the system, the process may treat the entities different based on their attributes. Attributes may change during a simulation. So you might stamp someone as hasn't been checked yet by a scanner. And after they go through a scanner, an attribute changes and now they have been checked. So later on in a process, that may affect whether they're sent back to get scanned again. So attributes can change during a simulation, but they ride along with the entities. And so they're not global variables. They're variables that are local to every entity. When an entity comes in, they have default variables. When they go out, they're lost forever. So they are things that help us discriminate among entities within the process. And so examples, and then activity versus delay, which comes up here. Both are durations, but again, activities are predictable. Activities are the things we can gauge with a stopwatch by watching someone. Delays, we don't know until we actually run the simulation. So delays are things that are outputs, activities are inputs. Was that a question? All right, so the question is, what's the difference between activity and event? Excellent question. An event is an instant of time that bookmarks activities. And so an activity is a duration of time. So for example, I arrived to the cashier. That instant I arrived at the cashier is an event. I spend time at the cashier. So how long is it taking for them to check my stuff out? That's an activity. But then once they're finished with me, that's another event. Cashier finishes. An activity is, well, no, an event is not even that special. It's just like there are two events. So there's the start of an activity and the end of an activity are two separate events. So I wouldn't call an activity a duration of an event. Our use of event is not thinking of an event like you might think colloquially, going to a cashier, like, you know, getting to the cashier or working with it is an event. Like it's exciting. It's an event. I'm going to be at the cashiers. But we're thinking operationally here, an event is just the instant I enter the instant the cashier starts working with me, the instant the cashier stops working with me. And so every activity has an event on both sides of it, but they aren't necessarily tied together. I wouldn't call an activity as a length of an event. Any other questions? Great question. That is a common confusion, the event versus activity thing. So some examples here. For a manufacturing system, entities might be parts that arrive at the system and eventually leave the system, possibly in a different shape as they were when they came in. The attributes might be features of the parts, their part number, their color, even the time that they arrive. They might be stamped with the time when they arrive. And that might be just so in the sim, we can keep track of how long they've been there. Because when they exit the system, we can then say, well, when did they arrive? And if you subtract, then you figure out how long they've been. The resources in this manufacturing system are going to be like the machines that each one of those parts stop at. And so there's a finite number of those resources inside there that are part of the process that the parts go through on going through this. Every time they stop at a machine, they conduct an activity if that machine is available. If that machine is not available, they'll have to sit and wait for that machine to become available. And that is the delay. So then state versus state variables, I think, is next here. So the events here are like machine failure. That's an event that doesn't necessarily have an activity, although the machine coming back up would maybe, you might think of that as like, well, then the activity might be how long the machine is down. Process completion, part arrival, these are all what I call events. The state variable would be the kind of phrase here, each machine is idle or busy. Like, so a variable is going to keep track of, it is the placeholder where it could either be idle or be busy. But the state itself is actually whether it is idle right now, like idle is a state and busy is a state. So as an example, in a 5 machine system, the state variables might be M1, M2, M3, M4, and M5. Those are the current activity, whether it's busy or idle, of every one of the 5 machines. But the state of the system is 11001, where 1 maybe encodes that they are busy and 0 encodes that they are idle. So the current state of the system is this particular set of numbers. The state variables are the kind of places where those numbers would be loaded into in your sim. And then you can ask, well, you know, why are machines idle? Why aren't they always busy? Well, that goes back to our delays. Some machines may sit there waiting for a part to arrive because that part is tied up with another machine. So that's kind of the purpose of our simulation, is to see how often that happens. How often are things idle? Because now we got to pay for them to be up and running when they need to be idle. But we also don't want them to be 100% utilized, because then if anything, you know, if any negative thing happens that might cause our throughput or might cause the number of parts to increase, then we might end up having a backlog there. So you always want some machines to be idle. So you might not want 100% utilization. Maybe you want 80% utilization or 50% utilization. So the reason we get non 100% utilization is because machines finish and parts aren't there yet because they're tied up in other machines, or they're tied up waiting to arrive. All right, so another example, university example here. I want to get to the stochasticity stuff here, so I'll just step through this quickly. We already kind of talked a little bit about this. Students are a great entity for a university model. You can think of a lot of attributes of a student that might be of interest to you as you simulate them moving through the particular classroom or the whole university. So GPA, major, et cetera. You can think of the things that cause students to have to wait. Is a classroom available right now? Well, if the classrooms are always there, but the students have to wait for the classroom to be available before they can come in, then that classroom is a resource. An instructor can also, if the instructor is not there, then the students have to wait for the instructor to become available. Activities, the class duration. So the students are stuck in that classroom for however long the class is. On average, the class is 75 minutes, but sometimes it's less than that. Sometimes it might be a few minutes more than that. So this is predictable. We would expect on average the class to be 75 minutes, but so it's the duration, not the time that it starts. So 10:30 isn't the activity, but 75 minutes is the activity. It's the predictable duration of the class. And then the delays, how long the students have to wait for those resources to become available. And I gave some state variable and state examples here, where the variables is like classroom, instructor, number of students. Those are all like variables. You can imagine X, Y, Z. And then whatever values they take, busy or idle, learning or proctoring, maybe the number of students listening at the time is anywhere from 0 to 104. So the individual number, or in this case, discrete number here, is the actual state of the system. Okay, so questions about that, these examples. I want to make sure that everybody's feeling more and more comfortable with entities, resources, activities, events, and the notion that a delay is an output of a simulation model, and an activity is a predictable input. Okay. All right, so let's wrap up with how we how we actually make these activities work. So the basic symbols that we're going to use here that I've kind of shown you so far is this kind of looking sort of trapezoid looking thing here is what I'm going to say is where we create the entities. So the big thing that we drill down and do here is how long in between each entity there is. And so the idea here is that we're going to model the inter-arrival durations of entities there. And this rectangle box here, that's where we're going to view as where entities are processed. So resources will live inside these boxes, but also there are arbitrary delays that you can add to entities as well inside these processes. But this is where we put the resources here. So activities take place inside these boxes here. There are these diamonds here. So this is like flowchart symbols, where those are going to allow entities to take different paths. And so we can put inside here either deterministic rules, entities that have certain attributes go out one direction, entities of other attributes go out another direction, or we can make it random. 25% of the entities go out one direction, 75% go out another direction. They're drawn this way with only a couple of different outputs, but you can have an arbitrary number of outputs. And so there's some graphical embellishments in ARENA that will indicate that entities might go out one of 10 different paths, for example. So just in general, whenever you come to a decide block, a decision point where they could go in multiple different directions, you're going to see one of these. And eventually entities reach one of these, which kind of do the opposite of the create block there. They're dispose the entities, they just remove the entities from the system. And so they don't really have any function other than just telling the system that the entity's gone, and it free, so it doesn't have to keep track of that entity and the events that are associated with it moving through. So from these basic process blocks here, state changes happen in these blocks here. So events are generated by those two blocks. And so I skipped ahead of here. So events are generated by blocks that look like this. So the events are generated by passengers that arrive and by how long it takes to process those passengers. And so we then need to focus on how to model the stream of passenger arrivals, and as well how to model the time it takes to move through each individual resource. And so that's what we're going to end up sort of focusing on as we build these stochastic models. And so with those two things combined, the delays that come out are how long they may wait in line before they can enter into this resource. So we've got activities here, delays there. And so that's all that I'm summarizing down here. All right, so what I want to get to here, which I may end up picking up with next time, is basically, so what do we mean by stochastic simulation models? So where does the stochasticity come into play and why? So this is sort of our main modeling approach here, where we want to build a simulation model like this that captures realistic variation in passenger experience. And if you think about where that variation lives, it lives in the time it takes for them to arrive, how long between arrivals. It also takes place in how long it takes for them to get through these resources, to actually go through these processes. And then also the randomness can show up in how often they go down one branch or another. So these are the three places where variation can be introduced, where some entities will have a very different experience than other entities, and we need to model that properly. Now, how do we end up choosing a good model of variation? So that's kind of the big question here. What are the real causal factors that determine the passenger arrival time? If we were trying to model a perfectly accurate model of reality, really implement a real airport system inside our simulation, then we would need to have, all of the kind of the narrative of what goes on with airport arrivals. So somebody might arrive, an hour before their flight. So they show up, here, maybe that's responsible, maybe that's cutting it a little bit close. You might find that there is another group of people, maybe they have one child. And so they would normally come to the airport at this time, but because they had their one child and they didn't really know that it was going to take so much longer getting the kid ready for the airport, so they end up coming a lot later. You might have another family that, say, has 2 children, and because they have 2 children, they're more practiced, so they end up coming much earlier. Then you've got maybe somebody else who's just always late to life, like me, and they sort of show up, pretty close to their flight. And then finally, you've got in your string of arrivals somebody else who is on a totally different flight. But as far as we're concerned, coming to the airport, they're grouped in with all of these arrivals. And so this is kind of the inter-arrival stream that goes into an airport. So there's a lot of these details here that we need to figure out. How do we capture this realistic variation? So one approach is we could say, well, let's just look on average here. This is kind of the system dynamics modeling approach. And we get on average 5 passengers per hour. So on average, the inter-arrival time between every passenger is 20 minutes. So one approach that we could do is to just put 20 minutes exactly in between every simulated passenger. And that might be fine enough for some problems, but it doesn't have any of that variation that really can make or break a lot of systems. This will just give us the average behavior of these systems. So we really would like to have that variation in there. So how do we get that variation? Well, the deterministic way is we would have to come up with a function of arrival time or of inter-arrival time that maybe is parameterized by the size of the family, the occupation, the distance from home, the flight number, all of these different things. We have to sort of build this long model to sort of say, based on the type of person arriving, when do we think they would arrive relative to everyone else? And it might be possible to build a mathematical formula for this, but it's going to be very hard to get it right. And even if we get it right for Phoenix, it's probably going to be wrong for Washington, D.C., and so on and so forth. And so building a deterministic model of variation is probably not a good path to go toward if we want generalizable insight. So what do we do instead? Well, we can observe here that, where did this formula come from? We can observe here that, well, if I look at the inter-arrival times in real passenger data, they really look like draws from a random number generator. They look like if I were to roll a die, I could say, well, I'm going to roll a die. Whenever it comes up 6, I'm going to use this inter-arrival time. Whenever it comes up 2, I'll use this inter-arrival time, and so on and so forth. You could turn this into kind of a Dungeons and Dragons game or any sort of board game where you could associate different inter-arrival times with different sides of the die and just roll the die. And you know what? The outcome would not look very different, as long as, just like in that Dungeons and Dragons game or whatever board game it is, as long as I've got kind of the right schedule of inter-arrival times to each side of the die, then I can manage to simulate the Phoenix airport pretty well. I just need to figure out how to assign those correctly. So, most of the time I'll get something close to 20 minutes, but sometimes I'll get 40 minutes, sometimes I'll get 5 minutes. So that's what I need to do, is to sort of design that dice schedule to give me realistic variation out. And this is what I'm going to be referring to here as stochastic modeling, building models that use randomness instead of deterministic rules. Stochastic is not a synonym for random. Other people might tell you it is. They're just being, that loses the nuance. Stochastic comes from the Greek for guess or conjecture. So back before this modeling approach, people did everything deterministically, and there came a set of systems where they become unbearable. And then there was a paper that was written where the mathematical modeler said, I'm just going to guess, without actually caring if it's real, that the real process underneath it all is random. And if I use a random model instead, I can get this results that look just like the real system, but I have to do a lot less work. That's where stochastic comes from, using the conjecture that the system is random without caring about whether the system actually is random. So we replace a fine-grained understanding of details with a conjecture that the behavior is just fundamentally random. It's quantum mechanical or whatever you like. So by doing so, this reduces our modeling burden. So we don't have to deal with all of those details. We just have to get roughly the distributions right. So that distribution of those die rolls might only have one or two parameters, a mean and a standard deviation. Whereas that deterministic rule for interarrival times, I'd have a parameter based on family size, based on occupation, all those different things, and who knows. So I replace 20 parameters in the deterministic with 2 parameters in the random case, because the random case gives me natural variation. I just need to shape it so that it looks like the data that I actually get in real systems. All right, so I'm going to end there. I'll give you an attendance question, and then I'll be happy to take questions, but I don't want to keep you guys anymore. So there's only one question for today. So the QR code will come up here in a second. And the question that I have for you is, roughly speaking, what is the kind of translation of the word stochastic? What does stochastic mean? And you can use one word for this. Like I said, it's like the Greek for this or that. You can use the this or that. It's fine with that. And I'll leave that up there. And that's all I've got for you today. Happy to take any questions. Are there any questions from here or from abroad? Checking the chat here. If not, hope you guys have a good weekend. Remember, lab is due on Sunday. I think there might be, there's probably some ICA opportunities coming up, I think, for next week. I forget if it's B1 or B2. Homework, if you like to start on it, is available. If you've done the lab, one question of the homework is very much like one question of the lab. So you'll be ready to do that. All right. Thanks for your patience. Yep, 1 second. Sure. Just give me 1 second. I just want to answer a quick question here. Sorry. Yep.
So for the lab, on like the entities and stuff, do you want like sentences for the?
You can just give me a, similar to like I did here. You can just give me like patience.
Okay.
It's fine.
I just wanted to make sure it's right. I had it all pretty much right now. I just didn't know if I need to make sentences or just like pretty much just listing stuff.
Yeah, listing is fine.
Okay. Thank you.
Yep.
A few days ago when you graded the assignments, I got a 0 on this one, even though I didn't miss a class or anything. I'm not sure what this was exactly.
Well, if your responses didn't sort of fit with the questions, I might have given you a 0. Send me an email and I can review and take a look.
Okay, sure. Thank you.
Okay.